Welcome to the presentation titled Making Sense of Things That Don't Make Sense. I'm Michael Trainer, a Senior Support Engineer at GitLab. I've been a team member since 2021 and I'm based in Queensland, Australia. This presentation is going to focus mostly on support engineering and how to troubleshoot problems in that domain, but this can also be applicable to other domains as well. Solving problems is hard. Doing so without all the necessary information is even harder. Let's try to navigate through the uncertainty. The goal of this presentation is not to help solve specific problems, but how to approach problems in a repeatable way that helps to solve problems quicker. I actually wrote most of this material back in 2023. I was self-conscious about sharing this material until I had a bit more tenure at GitLab. I realized this might be valuable to share with the team, so here it is. It started as a list of things to remind myself during an investigation, and it turned into a presentation. This information is for me as much as it is for others. I'd prefer that most questions wait until the end, as there's space dedicated at the end for questions. However, if you need something clarified because it impacts your understanding of the material, please feel free to ask your question during the presentation. What is troubleshooting? So before we dive into how to troubleshoot, we need to understand what troubleshooting is. Luckily, Wikipedia has an awesome description of what troubleshooting is. To be honest, I could just show this slide and stop the presentation early. It succinctly boils down the key parts of what troubleshooting is. I've spaced it out for each sentence and provided my own emphasis to make each point easier to digest. Troubleshooting is a form of problem solving, often applied to repair failed products or processes on a machine or system. It is a logical, systematic search for the source of a problem in order to solve it and make the product or process operational again. Troubleshooting is needed to identify the symptoms. Determining the most likely cause is a process of elimination, eliminating potential causes of a problem. Finally, troubleshooting requires confirmation that the solution restores the product or process to its working state. Bringing order to chaos. Be logical and systematic in your approach. This requires forethought and planning. Having a methodology and structure helps to guide the investigation in a predictable and structured way. Identify the symptoms by asking for information and passing that information. We need to be strategic with our requests for information and our processing of it. Use a process of elimination to determine the most likely cause. Eliminating potential causes or factors saves time and ensures the investigation is productive. Ask specific questions to reduce the problem scope and troubleshooting. A smaller problem is an easier problem to grasp and solve. Confirm that the solution restores a product or process to its working state. Sometimes this is not always possible. In that case, we should always look for a solution that is acceptable to the customer. So where do we start? We first start with extracting maximum value from the customer's initial information, even if it's incomplete. Sometimes we already have all we need to start. We just need to look deeper. Don't downplay their observations. They know their problem best. They have first-hand experience with the problem and are impacted enough to ask us for help. Trust but verify. We need to trust the customer but verify what they're providing is correct. I've been humbled many times by what seemed like an outrageous claim. It actually turned out to be true. We need to be aware of our own assumptions and not let them get in the way. It's okay to have assumptions, but our job is to prove or disprove them. Analyze the problem nature and scope, and then ask for more details. We need to understand what the impacts are, the type of problem, how widespread it is, how often it occurs, etc. These details change the way we troubleshoot. Establish the facts. Think like a journalist. I chose the journalist analogy because troubleshooting is really investigative work. You're trying to piece together what happened from incomplete information, just like a reporter covering a story. Initially, I wrote an analogy of a police investigation of crime. but after careful review and feedback, we removed it because we didn't want to associate our customers with crimes. So imagine that you're an investigative journalist uncovering a complex story. Think about things like this. What questions would you ask the key stakeholders and participants? Think about how journalists interview people. They don't just ask what happened, they ask specific questions. What information would you seek about the circumstances, the timeline, or the relationships between parties? What kinds of evidence do you need to support your story? You need hard evidence. This is basic journalistic integrity. You don't publish something just because someone told you it's true. Journalists corroborate their sources and verify claims. In troubleshooting, this means don't just rely on someone saying that it's slow. Get metrics, timestamps, and actual data to back up the story. Also, the 5 W's are useful to consider. You may have seen them before and you're aware of them, but I'm just going to explain them in the context of this analogy. So who? Identify the key stakeholders and participants involved. Relationships are key. Understand what events occurred. We need evidence that they did occur. When? Establish a timeline with key events occurring chronologically over time. Where? The systems and locations involved in the situation. Map the connections. Why? Was there a change, an event, a previous failure that caused the current one? Don't assume consensus. The customer knows best about their problem and its impact most of the time. This is sometimes hard for technical people. We often think we know better. Our job is to understand and make sense of their observations and not judge them. They're doing their best to explain the problem in their circumstances. Confirm understanding early, as soon as possible in the process. There's nothing worse than realizing we're investigating the wrong thing late in the ticket lifecycle. Confirm understanding early and option, as problems evolve and get more complicated. Common understanding accelerates resolution, faster troubleshooting and fixes. When customers feel heard and understood, they become our allies. They'll give you better information and have more patience. It's not just good customer service, it's good troubleshooting strategy. Rephrase and verify. Explain the problem and its impact in your own words and ask them to confirm. We can think of Cunningham's law, which is the best way to get the right answer on the internet is not to ask a question, but to post the wrong answer. People will often be motivated to correct wrong information, which works in our favor in this circumstance. If we explain the situation in our own words and we're wrong, they will let us know. If we're right, then we know we're on the right track. Watch for XY problems. Are they describing symptoms when the issue is elsewhere? A classic example is, how do I restart the server when what they mean is the application is slow? Always ask, what are you ultimately trying to achieve, or what problem are you trying to solve? Make and record observations. Document what you see. Even seemingly irrelevant details matter. This is harder than it sounds because we're trained to filter information. I've learned to document everything I notice, even if it seems silly. Observations build the timeline. They become the foundation of your narrative. Every observation gets a timestamp and becomes a data point in your story. These observations become the backbone of your narrative. They tell you the sequence of events and help you identify cause and effect or correlations. Don't filter too early. Record first, analyze relevance later. We don't want to prejudge what's important early in the investigation. Include the mundane or obvious. These can be vital clues that could be missed. Timestamp everything. When did you observe it, and when did it happen? This gives you a specific window of time to start investigating and helps to determine the actual time frame to investigate, which might be larger or longer than you first anticipated. Build a narrative. Everyone likes a good story. It makes complex problems less intimidating. Our brains are literally wired to understand information as stories. When you have many different error messages and many system components involved, a timeline narrative makes it digestible. Instead of overwhelming complexity, you get, here's what happened, and then this happened, which caused that. Stories have structure. a specific time, a place, and participants interacting. Build a coherent narrative. Define the time, place, participants, and their interactions. Check for plot holes. Does your current story make sense? And when you find these plot holes, don't just ignore them because they're clues. Maybe they were actually two separate issues happening at once. Maybe your timeline is wrong. Maybe there's a third component you haven't considered yet. The inconsistencies in your story point you towards where you need to investigate next. Resolve inconsistencies. Fix the gaps in your narrative. I actually try to tell my narrative back to the customer sometimes in a timeline. The narrative helps them remember crucial details that they initially left out. Zoom in, zoom out. These terms are borrowed from photography, but they're perfect for troubleshooting. Zoom in means diving deep into specific details, reading individual log lines, checking specific configuration values, tracing exact code paths. Zoom out means stepping back to see the bigger picture, overall system health, business impact, whether you're even working on the right problem. You can get stuck in the weeds if you only zoom in, and you got so focused on one tree that you missed the forest burning down. Zoom back out regularly to reevaluate if you're spending time on the right things, making progress towards solving the problem, or going down productive paths versus dead-end side quests. Constantly reevaluate if your current lines of inquiry are fruitful and in service of the goal, which is solving the problem. Frequent zoom outs renew focus on the main goal. The zoom out isn't just stopping wasted effort. It's about getting re-energized. When you remember why you're doing this and what success looks like, it gives you clarity on your next steps. Be curious. Sometimes intuition trumps methodology. If something feels off, investigate it. You need to remain focused in your approach and flexible, which allows for random detours or testing of wild theories. Test your hunches, even if they seem unrelated to the main problem. Your prior experience can guide you. Look for the unusual. What's different about this specific case? Or what's different about the customer? This specific request, this timing, the group membership hierarchy. Channel your inner tester. What would break this? What edge cases exist? This comes from my background as a software tester. Good testers don't just follow happy paths. They ask, how do I break this? What would cause exactly this kind of failure? I've used this method many times recently to reproduce weird race conditions or bugs by breaking things in a controlled and methodical way. It's like reverse engineering the problem. Sometimes the answer is hiding in the details that you dismissed or missed. Don't assume everything is relevant. Test whether it is first. Embrace the learning opportunity. Problems are teachers. Unfamiliar territory is where you grow. Embrace what you don't know. Don't be intimidated when you encounter something completely outside of your comfort zone. Research with purpose. When investigating, you're building expertise. Curiosity over frustration. When you don't understand something, that's your cue to learn. And it requires a mindset shift. Instead of saying, I don't know Kubernetes, try, cool, I get to learn Kubernetes today. Instead of, this Postgres error makes no sense, try, I'm about to understand how Postgres really works. Ask why and how. Don't just fix it, understand it. And document what you learned. Not just the solution, but the new concepts that you discovered. Future you and your teammates will thank you. When we write public knowledge base articles, future tickets will be deflected. Everybody wins. AI is your friend, not your shortcut. I added this section because AI has fundamentally changed how we troubleshoot. The key is understanding what AI is good at and what it's terrible at. It's good at expanding your perspective. You can ask AI to suggest alternative hypotheses or identify blind spots. AI excels at generating alternative hypotheses you might not think of. It's like having a brainstorming partner. But like our fellow colleagues and ourselves, it's not infallible. Treat it as such. AI can guide you through unfamiliar territory. You can let AI explain concepts or technologies that you don't know. When I encounter something completely outside of my domain, like what does this Kubernetes error actually mean, AI can explain it in terms that I understand, suggest what to do next, or translate technical jargon into plain language. It's like having a patient mentor. You can use AI as a rubber duck, brainstorm plans, or talk through your troubleshooting approach. You may know the term rubber duck debugging. If not, it involves talking to an inanimate object like a rubber duck about your problem, and in doing so, you can improve your thinking and decision-making process. AI is a much better rubber duck. Instead of hearing your own voice, you can have a dynamic conversation. As much as AI is good at things, there are pitfalls that we have to be aware of. AI should assist you and extend your investigation and not be the sole form of troubleshooting. AI isn't a replacement for thinking. You still need to apply the systematic approach. AI isn't a magical oracle. We are the directly responsible individuals, or DRIs, for the problem, and we can't outsource that. AI can accelerate confirmation bias if you ask leading questions or only seek supporting evidence. This is subtle but crucial. If you ask AI, why might this be a database problem? It'll give you a dozen reasons why it could be the database, even if it's not. You've primed it to confirm your existing theory. Instead, ask, what could cause these symptoms? And let it suggest multiple possibilities, including ones that contradict your current thinking. Don't skip the verification step. Always trust but verify. AI can help gather information, suggest hypotheses, explain concepts, but you're still the one making the decisions, testing the solutions, and understanding the bigger picture. The moment you stop thinking and just follow AI's suggestions blindly, you're no longer troubleshooting. AI troubleshooting strategies. I've added 4 approaches here to choose from. There are many, but these are just ones that I use on a regular basis. The minimalist approach. Avoid confirmation bias and let AI generate fresh hypotheses. This seems counterintuitive, right? We usually want to give AI all of the context that we have, but sometimes that context includes our biases and assumptions. It might cause us to fall deeper into unproductive rabbit holes. You can feed AI additional context during the discussion. There's a full context approach, which involves providing all relevant information and context up front. This can be useful when you need to move fast and you're confident in your investigation direction, or if you're totally stuck and you need some direction. When you have hundreds of lines of logs and multiple error messages and a complex timeline, AI can spot correlations you might miss. It can also make summaries that help you make sense of the complexity. The devil's advocate approach. Ask AI to argue against your current hypothesis. This challenges your assumptions. This is also uncomfortable. It's also valuable. When AI challenges your theory, you have to articulate why you believe what you believe. Sometimes you realize your evidence is weaker than you thought. Other times, defending your position helps you identify what additional evidence you need to confirm or refute your hypothesis. And the step-by-step guidance approach. Get a structured checklist for unfamiliar domains. This is perfect when dealing with something completely outside your comfort zone. Instead of fumbling around randomly, you can ask AI to give you a structured approach. It's like having a troubleshooting playbook for domains you're unfamiliar with. This helps to identify where you might want to focus your investigation and start eliminating lines of inquiry that are not relevant. The main message, the point isn't to memorize these approaches, but to understand that AI is a flexible tool. Match the approach to your needs. Reproducing the problem, why it matters. Reproduction allows you to verify both the problem and your proposed solution. It confirms the problem type. Is it consistent, intermittent, or truly random? You can't know which approach to take until you understand the problem's nature. Shapes your strategy. Different problem types require different approaches. Enables controlled testing. You can test potential solutions safely. And we're not only testing the solution, we're testing how the problem is reproduced. Eliminates guesswork. Moves from theory to observable reality, and builds confidence, both yours and the customer's, in the proposed solution. When you can reliably make something fail and then make it work, both you and the customer know that the problem and the solution are real. There's no uncertainty. It also helps our engineers understand the problem and allows them to fix any bug reports quicker. I've seen many bug reports sit in backlogs indefinitely because they're vague and not reproducible. When you can hand over exact reproduction steps, developers are more likely to identify and fix the root cause. Alright, question time. This is going to make a bit more sense in the synchronous session, but this is asynchronous. It's also to test if people are still awake at this point. So the question is, what are the main things that you think about when trying to reproduce a customer's issue? I'll leave some time here for you to think about it, and then we'll move on to the next slide. Alright, I think that's enough time. So let's move on. Aspects of reproducing a problem. Keep in mind that these are high-level aspects to reproducing a problem. We'll dive deeper into each of these on their own slides. There's 4 main aspects. The first one, reproduce the scenario. Second, reproduce the environment. The third, reproduce the data conditions. And 4, reproduce the architecture. Reproducing the scenario. Sequence of events and actions. The order matters. The scenario's sequence of events might be triggering a very specific condition. Timing patterns and conditions. Load patterns, batch job schedules, race conditions, session timeouts, cache expiry, peak usage times, etc. Finding a time-based pattern to the scenario can save a lot of time for some types of problems. An example is I helped with a ticket recently where a CI/CD job was failing. It used Docker service containers. The health check of the service container was fine, but when the job started executing, it failed. My hypothesis was that the service container was being killed between the health check, which was positive, and the start of the job's execution. I tested that hypothesis by building a custom Docker image that mimics normal service behavior initially, but then self-destructs after a predetermined time using a time bomb type script. This approach allowed me to precisely control the timing window. The service container stayed up long enough for the health check to pass, but died before the container linking phase. The result was an error message exactly matching the customer's error message, successfully reproducing the problem and allowing us to test our solutions and workarounds. User journey in context. What were they trying to achieve and accomplish versus what are they actually doing? This is about understanding intent versus action. Understanding what they're ultimately trying to achieve helps you spot when they're taking an unusual path. Their problem might be a training issue and not a technical issue. The best kinds of problems are not problems at all. Reproduce the environment. Match their software stack as closely as possible. Version mismatches are a common cause of works for me type of issues. And here are some things about the environment you should consider, like versions. This can be versions of GitLab, GitLab Runner, Kubernetes, Docker, pretty much everything that is within the scope of the problem. Configuration, settings, integrations, customizations, product tier and feature flags, what is enabled or disabled, dependencies, external services or third-party tools. The problem may be related to specific versions of components or incompatibilities between versions, specific configuration settings or conflicts, feature flags that have been enabled or disabled. Reproduce the data conditions. Data size, content, complexity, and format can trigger specific issues. Create test data that mimics the customer's data characteristics. Don't just replicate the process, replicate the actual data. This is where a lot of troubleshooting falls short. We test the happy path with clean, simple data, but production data is messy. It has edge cases, unusual formats, unexpected sizes. The process might work fine with your test data, but break with their real-world complexity. Data volume. Small test versus production scale datasets. Testing with 10 records is different from 10,000 records. Pagination breaks, queries time out, memory usage explodes, UI becomes unusable. I've reproduced performance issues when replicating similar data volume and complexity as the customer. I was able to provide empirical evidence of performance bugs where increases in data volume directly correlated with higher response times. You can even plot this data in a graph to better highlight the problem. Data characteristics, special characters, encodings, formats. We need to confirm whether the format or the content of the data itself is causing the problem. Example, I had a ticket where a project on GitLab.com could not be deleted. I wasn't able to figure it out initially, so I raised a request for help issue. Even then, the backend engineers were unsure of the problem. I went back to basics and I took a look at the project's characteristics. I noticed that the project description was not only long, but had some special characters in it. I ran a few tests of my own with similarly sized complex project descriptions, and it turns out that the length alone reproduced the problem. You could create a project description of that length, you just couldn't delete the project with that length. So removing or truncating the project description allowed for the deletion to succeed. This analysis allowed for a bug report to be quickly raised and fixed. Data state, existing records, permissions, relationships. It's not just the data itself, it's the relationships between entities and objects, the specific state or transitions of state. Sometimes the irrelevant details are the key. And respect data security. Create realistic test data when you can't use actual customer data. In most cases, you can't just copy production data, but you can create realistic test data that matches their patterns. Try to determine their data requirements based on the points above and replicate those patterns safely. Reproduce the architecture. This is often the last piece of the puzzle. You've matched versions, replicated the scenario, created similar data, but the problem still won't reproduce. That's when you need to look at the infrastructure layer. Architecture differences can create problems that are completely invisible until you match the exact setup. You need to think of things such as the provider. Examples are AWS, GCP, Azure. There are cloud-specific behaviors, features, and bugs. Architecture pattern, single node, distributed, cloud-native hybrid. Single node setups have different failure modes than distributed systems. Distributed systems add complexity, and this complexity is where problems can occur. Customers may also implement architecture patterns that are not recommended. Resource constraints, like CPU, memory, disk, network limits. Problems that are invisible with abundant resources become obvious under load. Memory leaks, CPU spikes, disk I/O bottlenecks, these only often occur when resources are limited. Network topology. Although we don't provide direct support for the network setup, it's useful to test whether this may be a contributing or causing factor. And also we might want to consider things like geographic distribution, which can impact latency, and there might be regional differences. Code is the best documentation. And there's a caveat here. This requires some programming literacy, but even basic code reading skills can be incredibly valuable for troubleshooting. You don't need to be a developer. You just need to be curious enough to trace the logic. The more you expose yourself to reading code, the more comfortable you will be reading code in the long run. Documentation shows intent, how things should work in theory, but the code shows reality, how things actually work in practice. During troubleshooting, I often consult the actual code base because our documentation represents an aspirational view of how things should work. The code, however, shows exactly how it does work. There's always a gap between the intended and actual implementations. Sometimes the truth lies in the middle ground between how things are and how they're intended to be. GitLab is open source. Embrace this advantage and use it for troubleshooting. Having access to the code is a huge benefit to troubleshooting. This is the difference between black box and white box testing. Black box tests the functionality without consideration for its specific implementation. White box tests consider the internal code structure, code paths, etc. With open source, we can see inside the system instead of just guessing from external behavior. This lets us target specific code paths and conditions during our reproduction phase. Use git blame and commit history. Understand why code changed and when. Oh, I forgot to say, code is never out of sync. It is the current implementation. Documentation can become outdated, but the code is literally what's being executed. Use code to guide troubleshooting and also to inform reproduction of the problem. Understand what conditions trigger specific behaviors. Think about the aspects of reproduction we discussed earlier. This point speaks to reproducing the scenario and the data conditions to hopefully achieve a specific outcome based on our analysis. Code can reveal edge cases, conditions and validations that might not be documented. Conditional logic, error handling, state machine transitions, event hooks, validation rules, these are all explicitly defined in the code and can guide your troubleshooting. Don't assume you understand the code. Reading code creates assumptions that must be verified like any other hypothesis. This is crucial. Just because you've read the code doesn't mean you understand it correctly. Code reading creates assumptions about behavior, and those assumptions need to be tested, just like anything that we do in our systematic approach. I've been wrong many times about what I thought the code was doing versus what it actually does, so always keep an open mind. Logs are the currency of troubleshooting. They're objective evidence of what actually happened and not what people think happened. Logs are crucial. They're the foundation of any investigation. Logs tell the story, what happened, when, and sometimes why. Correlate across components when multiple systems are involved. Modern systems are distributed. GitLab connects to Redis, Postgres, Sidekick, and other external services. An error in one component often cascades to others. What you might initially see as a cause might be a symptom of an earlier or a larger problem. Match the time period. Ensure logs cover when the problem occurred. This might sound obvious, but it does get missed. Always verify you're looking at the logs that cover the exact time frame when the problem occurred or was observed. Make sure it's the correct time zone as well. Get all participant logs. Every component in the chain matters. Don't just look at the component that's throwing the error. Look at everything in the request path. Each component can contribute to the problem, and you need the full chain to understand what happened. Correlate log events. Start by searching by time. Find errors occurring in similar timeframes as the problem. Often you'll find related events that happen slightly before or after the reported problem time. The user may see the symptom at 2:15, but the cause might have started at 2:12. You might notice a big spike at a certain time, but that doesn't necessarily mean that the problem started then. Search by context, events that match your investigation criteria. Once you have a time window, search for a specific context, user IDs, project names, IP addresses, error pattern strings, etc. Zoom out and zoom in. Look for specific things, but also look for patterns. Start broad. Look for overall patterns in the time window. Are there high error rates, unusual traffic patterns, resource spikes? Then zoom in on specific events. Maybe there's a pattern. Look for the presence or absence. Sometimes what's missing is the clue. Depending on the problem, we might see things we shouldn't, or things we see, or the things that we should see are not there. Ask yourself what you should be seeing versus what you are seeing. Also use identifiers to correlate across same or different log sources. Things like correlation IDs, job IDs, pipeline IDs, Sidekick job IDs, container IDs, or pod names. Keep your cool. So you have to acknowledge the pressure exists, but don't let it drive your decisions. Breathe and reset when you feel stuck or overwhelmed. When you feel that panic is creeping in, when you've been staring at logs for 30 minutes and nothing makes sense, literally stop. Take some deep breaths and step away from the screen if you have to. Panic literally narrows your cognitive focus and makes you miss obvious things. Stay curious. Pressure kills curiosity, but questions lead to answers, and assumptions can often lead to wrong solutions. Separate urgency from panic. Urgent doesn't mean abandoning good practices. Urgent means important and time sensitive. You can move quickly while still being systematic. Communicate transparently. Customers prefer bad news to silence. I don't know yet, but here's what I'm checking next is infinitely better than radio silence. It shows progress, demonstrates competence, and buys you time to work. Trust your process even when others want shortcuts. Know when to escalate. Escalating isn't due to an individual failure. It is just the next logical step in the investigation process. We're a team and we need to leverage the resources, experience, and knowledge of that team. Escalation is a skill and it's not a failure. Because remember, we can't know everything and we are a team, not a collection of individuals. Here are some early escalation signals. You've exhausted your systematic approach without significant progress. The problem requires domain expertise you don't have. The customer impact is escalating faster than your investigation. How to escalate effectively. Summarize what you've tried. Save others from repeating your work. Explain the customer impact and timeline pressure. The impact and timeline can help people prioritize the response appropriately. Be timely. Don't wait until you're completely stuck or the customer is frustrated. If you're stuck and it's something outside of your expertise, you need to escalate. And definitely don't wait until the customer is angry. Escalating before the customer gets frustrated looks much better than escalating because the customer demanded a manager. Target the right group. Identify who has specific expertise you need. The more specific you are, the faster you'll get to the right person. Have a specific ask. Not, I need help, but can you help me understand why X is happening when Y occurs? Ambiguous questions get ambiguous answers. People are more motivated to assist when the problem and request is understandable and it seems achievable. Consider customer tickets that lack actionable information and compare that to what you're asking. Would you be satisfied with receiving a ticket with that kind of information? If not, structure your ask and ensure it has the right information. Capture what you've learned. Document your journey, not just the destination, such as what you tried and why, even the dead ends, the key evidence that led to the solution. Write for the next person who encounters the problem. That person could be you. Make your fellow colleagues successful, not just informed. Update existing documentation if you found gaps or inaccuracies, and don't let the next person fall into the same traps. If you had to learn something the hard way because existing documentation was wrong or incomplete, fix it. Don't let the next person waste the same hours you did. Fix the absences or inconsistencies as you identify them. Create knowledge base articles for novel problems. If this was a hard thing to solve, someone else will face it too. Include preventative measures when possible, like how to avoid this problem. We are our values. GitLab values are very useful in the troubleshooting process. Let's look at some of our operating principles and see if they help us troubleshoot. Spoiler alert, they do. Serving our customers. The relevant operating principles are assume positive intent, kindness, say sorry, and no ego. Customer management is problem management. Expectations and satisfaction matter. Assume good faith. They're doing their best to help, usually. Communicate with empathy. They may be under intense pressure to get this resolved. Separate the work from the person. Be kind even when frustrated, to the customer and to yourself. Own mistakes quickly. Apologize and move forward. Check your ego. Focus on the problem and not yourself. Knowledge isn't everything. The relevant operating principles are, it's impossible to know everything, self-service and self-learning. Not knowing is the first step to knowing something. So don't be embarrassed if you don't know, because it's the first step. As long as you follow it up with the next step, which is learning. Approach matters more than knowledge. It's okay not to know things. So the approach you take is a lot more valuable than the knowledge that you have. The knowledge is important, but how you approach the problem is invaluable. Uncertainty is guaranteed. Roll with it. Perfect information doesn't exist in our world. We never have the complete picture. Optimize information access. Get better at finding information and making sense of what you have. Keep an open mind and be prepared for failure. The relevant operating principles are: write things down, low level of shame, articulate when you change your mind. Use the scientific method, observations, hypotheses, and thorough testing. I mention this because we shouldn't be emotionally invested in a specific outcome or a theory or a resolution. We should go where the observations and the test results tell us. We should be open to new possibilities and change our view based on new information and evidence. Explore different paths. Don't fear going down the wrong road. And expect to be wrong. You will be wrong more often than you're right, so adapt quickly. Document everything. Observations, hypotheses, and tests reduce the problem scope and help others. Balance the need for problem solving and customer results. The relevant operating principles are: customer results, sense of urgency, have ownership and accountability, reach across company departments. Customer results do not equal perfect solutions. Workarounds and mitigations count. Mitigate first, solve later. Reduce customer impact while investigating. Engage help early. You can't solve everything alone. Take ownership with urgency. This drives better decision making and gets better results. And keep communicating, even when there's no progress to report. Own your troubleshooting journey. Relevant operating principles are: manager of one, operate with a bias for action, and give agency. Take initiative in investigations. Don't wait for someone to tell you what to check next. Own the problem, from initial customer contact through resolution and documentation. Make decisions autonomously. Use your judgment on investigation paths and escalation timing. Empower yourself to learn. Research unfamiliar concepts, dig into new technologies. And trust your process. You have the framework and skills to navigate uncertainty. That brings us to near the end. The key takeaways are: be systematic, but stay curious. Balance methodology with intuition. Trust but verify. Applies to customers, AI, and your own assumptions. Zoom in and zoom out. Don't get lost in the details. Document the journey. Help the next person, including yourself. Escalate early. It's a skill and not a failure. Keep your cool. Panic leads to missed details and rushed mistakes. That concludes the presentation for making sense of things that don't make sense. The goal isn't to memorize every technique. It's to develop a systematic mindset that helps you navigate uncertainty with confidence, ask better questions, find solutions faster, and learn from every problem that you have. Questions?